Okay, so we now begin with section 6.5, which is the stress and deformation in a twisted elastic circular shaft. So just put it up like this. Okay, and we'll just go through what we have gone far in this particular chapter. So in the preceding three sections, we have considered the geometry of deformation. Remember how we used symmetry arguments to find out the value of shear strain tau theta z, and then we found the stress strain relations using the Hooke's law for the cylindrical coordinate system, and finally we had the equilibrium equations for a twisted circular shaft, and the material which we had taken was isotropic and linear elastic, which was obeying the Hooke's law. So they were summarized in equation 6.2, 6.3 and 6.4. Okay, 6.2 was the shear strain, 6.3 was the Hooke's law where you had found the values of the stresses, and 6.4 was the equilibrium equations. In this section 6.5, we would combine these physical results in a manner which will produce the interrelations which are of interest to us. So what are the relations which are interest to us? The relation between tau theta z and mt and phi and mt. Okay, these are the two things which we would want, and you can see why. I mean, consider this says a spring. You would want to apply a force F, and then you want a certain delta x compression in this. Similarly, you would want to apply a twisting moment mt and expect this angular movement phi. Okay, so and the same you would expect. So this is like for applying a load and getting a suitable amount of deflection, and in this one you would apply a fixed load, and then you would want to see how much shear stress is generated. And since this is the only stress component which is relevant, that's why we have written it like this. And this is important because if this is of a very high value, then your shaft might break. Okay, so that is why you want to understand how this tau theta z will vary with mt, and you must have done that. I mean, if you use a screwdriver to insert a screw, say between to join two materials non-permanently, that's called a non-permanent joint with a screw and a nut. If you twist it too hard, after a while it would break. Okay, or something or the other will break. So that is something which you have to keep in mind when you do this. So that's why, so we would know how much shear stress would be generated only once we have a relationship between mt, because this is what you again apply and this is what you get. This is what you apply, this is what you get. So both of these objective things should be of a desired range. It should not be very high or very low depending on the need. Okay, now if we substitute tau theta z from 6.3, so 6.3 was the Hooke's law, and you want to put it now into the equilibrium equation, which is 6.4. So let me just write 6.3. Tau theta z is equal to g gamma theta z is equal to gr d phi by dz. So this was 6.3. All other stress components were 0, and 6.4 was I think over here, right? This was 6.4. So you want to put 6.3 into 6.4, then you would get mt is integral over area A. You will have r, and then tau theta z would be gr d phi by dz dA. Okay, this would imply that mt is equal to g d phi by dz. We can take it out because it doesn't depend on the area, and a into r square dA. So this r square dA, the integral of it, you may recall from your course in mechanics APL 100, that this can be written as Iz. Okay, so this is a polar moment of inertia of the cross-sectional area about the axis of the shaft. This particular quantity is Iz, and it's the polar moment of inertia of the cross-sectional area about the axis of the shaft. So you have already known about this term. Now if you want to calculate this value for a shaft of radius r0, okay, so there's a shaft of radius r0, diameter d, we can find the integration and get that Iz is equal to pi r0 4 by 2 pi d 4 by 32. Okay, so that's how you would get a d phi by dz, and that would be equal to mt divided by giz. Okay, so g phi by dz you can write like this. Now you want to eventually find this, the relationship between mt and tau, or mt and phi. So for doing that you would have to just integrate this. So phi would go mt by giz dz, and that would go from 0 to L. Okay, because delta z is a small slice and it goes from 0 to capital L, which is the length of the shaft, and phi is something which you would get in radians after this, so this would just make it mt L by giz. So this 6.8 essentially gives you this, the relationship between phi and mt. So now you would know that if you want to achieve a suitable angular rotation, how much of angular twist, how much of twisting moment you must apply. Okay, and that's how you would go about it. And okay, so that's the first part of it. Now the next part is about trying to find this thing, the relationship in tau, theta z and mt. So all we have to do is substitute this thing into this 6.3. Okay, so let's see, tau theta z is equal to gr, d phi by dz is mt by giz, and this would imply that tau theta z is equal to mt r by iz. Okay, so that gives you the value of the shear stress with the twisting moment, and as you can see it depends on this parameter r, so it would depend radially, and so it's a linear relationship. Okay, and so we'll analyze this result. This is 6.9 now. So we have considered the problem of twisting of a circular shaft and obtained relation 6.8. 6.8 is over here, between the applied twisting moment and the resulting angle of twist, and relation 6.9 between the twisting moment and the resulting stress distribution. The stress and strain distributions 6.2 and 6.3 on which these were based do in fact satisfy the fundamental equations of elasticity, so that for every small element the requirement of equilibrium of geometric compatibility and Hooke's law is satisfied. Furthermore, so they all satisfy these conditions which was laid out in 2.1. Furthermore, the boundary condition of no stress on the outside cylindrical surface is satisfied. So there is no stress on the outside cylindrical surface because the shaft, if this is the shaft, there is no stress on the outside. Okay, the boundary condition no stress on the outside cylindrical surface is satisfied. The only possible shortcoming of our solution at the ends of the shaft. Okay, so if our solution is to be, so let's see what that shortcoming is. If our solution is to be valid at the ends, then the externally applied twisting moment must actually be distributed according to the pattern of 6.9b. So this is the pattern shown by 6.9b, and this is what you should eventually get. Okay, theoretically this is what we are getting. Now what happens is that in many practical cases, okay, when MT is applied by the jaws of a wrench, okay, so you want to sort of this is the bolt, you have a nut, okay, and then you have a wrench, and you want to apply this MT. The actual stress distribution at the end, although statically equivalent to MT, is widely different from that of figure 6.9. So this is something which you would learn actually when you learn about screws, nuts, bolts in your machine design course. Okay, you will see that if this is the head of your nut, how the stresses and moments are in this case over there. So it is very different than this one point moment acting about one point. Okay, so in reality, you will see that this wrench, for example, this will apply a friction force like this and like this, and eventually you will have something which is statically equivalent to MT but not exactly MT. Okay, so that is the difference over here. For most practical problems, this MT does not apply exactly like this. Okay, so but again, that's the whole point. Like, if by the Saint Venant's principle, which we have discussed before, if you have a statically equivalent boundary condition, then the solutions which are far away from the boundary are approximately the same. Okay, and that is the reason why these results are still taken and found to be working despite the boundary conditions being towards the end of the beam slightly different. And that's why I always insist, and you should always do it yourself, to stay away from the boundary as much as you can. Okay, so that even when the actual loading is different from what you have idealized, your answers would still be correct about finding the stress, about finding the strain, about finding the displacements or the twist. Okay, so that's why this is how we use. So one of the limitations, as you have seen, this 6.9 which you have found out, you cannot use this equation to find the stress at the ends of the shaft. If this is your shaft and this is your MT, okay, you cannot use this in, say, a region like this which is near the ends. You should constrain yourself to parts which are away from the boundary. So by experience you get to know how much away from the boundary you have to be able to use these results correctly. So there is no one line answer. It's just like when you say that you are taking this point very close or very far away from another point. So it's sort of that analysis. So it depends on case to case, experience by experience, but theoretically, in one word, you should always try to stay away from the boundary and into the bulk. Okay, so it is unusual to encounter situations in which the shape of the body and the loading imposed on it and the resulting deformations are so simple that an exact solution according to this theory is working. In most engineering situations, we would have to be content with the solution which does not satisfy all the conditions of elasticity exactly. So many a times you will come across solutions which are approximate, and so much so that they do not satisfy all the conditions of elasticity. And that is how things have been working, and very likely they work reasonably well, in the sense all the things which you see around you at this moment, the furniture, the walls, the automobiles, they do have their basis in elasticity. Okay, but it is not necessary that all of them exactly satisfy all the conditions of theory of elasticity, all those 15 equations which we had read about. Okay. So there are approximations. That's where Saint Venant's principle comes into the picture. Okay. Now, when we consider a length of the circular shaft to be a structural element, the relation 6.8 becomes the load deformation relation. Okay, that's obvious. So this is the load mt, this is the deformation. Okay, to be used in the third step of 2.1. So it is often convenient to state 6.8 in this form. So mt by, so I'll just write all this over here. Yeah, mt by phi is equal to giz by L. So this is just writing F by delta for a spring. Okay, that would be K. So this gives the twisting moment per radian of twist. Okay, this is the twisting moment per radian of twist, and the ratio is analogous to a spring constant, which gives tensile force per unit length of stretch. This ratio is analogous to spring force, which is tensile force per unit length of stretch, this one. The ratio in 6.10 is called the torsional stiffness of the shaft and is often denoted by the symbol K or C. So let's just use C not to get confused when I think so. So this is the torsional stiffness. Just like this is the stiffness of the spring. So we won't use the symbol K over here. For this torsion, let's stick with C because K is already taken. Some people also use kappa for it, but just to avoid any confusion between K and kappa, let's go with this. Okay, so the complete solution to any problem involving a twisted elastic shaft consists of establishing these equilibrium equations and of satisfying the load deformation relation, which you have just seen, this one, 6.10. Okay, so let's see how that works in a problem. Okay, so you have this example 6. Example 6.1. So this is about lathe machines. So you have two small lathes which are driven by the same motor through a 1 centimeter diameter steel shaft. This is going to one lathe, this is going to the second lathe. This is the motor which is driving this, and there is a steel shaft of 1 centimeter diameter, this one. Okay, now we wish to know the maximum shear stress in the shaft due to twisting and the angle of twist between the two ends of the shaft. Okay, so you want to find the maximum shear stress and the twist angle of twist phi between the two ends of the shaft. So there are forces which are given to you, and the dimensions as well are given. So let's see how we can proceed to solve this problem. First thing is, we always want to, we have the actual problem. Now we want to have a model, an idealization of this. So to idealize the situation, we represent each pulley loading by its static equivalent of a force of 120 newtons. So rather than taking this 120, the total force you can take as 120. Okay, it's not the same, but it's statically equivalent. So this force is acting at a different point, this is acting at a different point, and this 120 is acting at a different point, but they are statically equivalent for this pulley. Okay, and for this pulley as well. So this is how 120 newtons is taken. Now we have to also consider a couple about the z-axis, and that would be 8 Newton meters. Okay, so you have this 100 and this 10 centimeter radius and 20 into 10 centimeter. So you would get an 8 Newton meter torque. Okay. So that would be the couple of 8 Newton meter, and that would be there in both the cases. The direction of the moment is already shown. So you can just take a R cross F for both 100 Newton and the 20 Newton, and you will get a direction and the value of 8 Newton meter. Now each pulley is supported by a pair of immediately adjacent bearings. So these are the bearings. If you don't know what bearings are, please have a look. Okay, so I think SKF is a very famous company of bearings. So just you can Google SKF bearings and look at a picture. What it helps, bearings help you to achieve like a smoother rotation, like the ball bearings in your cycles which get worn out over time is one example of bearings. Then there are roller bearings also, which is again used in your cycles, but at the same time you also have something called a journal bearing, in which you have a shaft. So if this is, say, the stator, this is the rotor. What you do is you fill it up with a fluid, this is called a lubricant, and so that there is no direct contact between the stator and the rotor. So this is also another kind of bearing. So this bearing is called a journal bearing. So we don't know what kind of bearing it is, either journal or the ball bearings, but we know that it's a bearing, and that's what we need to know for now. So this is also again one of the things which perhaps might come up in your course in machine design. Okay, so there's a very famous book by Shigley, or it is called Shigley's, I don't know, for machine design book. I think that's the excellent, very good book at this stage. Okay, so each pulley is supported by a pair of immediately adjacent bearings. We make the idealization that the 120 Newton transverse force is balanced by the bearing reactions in such a way that there is negligible shear force and bending moment transmitted beyond the bearings. So that is one of the purposes of this bearing. It makes this rotation so smooth that practically the friction is negligible, and because the friction is negligible, you should not have a shear force over there, and that is why this is what we can assume, that there is no shear force or bending moment transmitted beyond the bearings. Okay, so there would not be any shear force or bending moment in this region, sorry. Yeah, okay. In this case, it is only necessary for the motor to supply a torque ma. So ma is what the motor is supplying, and then you have this very long shaft which you have taken. Okay, fine. Now this is, I mean, you can see why this is there. I mean, so if this is a stator, this is a rotor, and if you have filled it up with a lubricant, so this is normally some sort of a viscous fluid, okay, which changes viscosity with temperature, and then that's called, it somehow balances out, so that the temperature rises, the viscosity will change accordingly. So the friction gets reduced because, even if friction was acting, say just an assumption, depending on the direction of rotation, this friction value would be reduced a lot compared to if there was a direct contact, and that's why it is reasonable for the shaft. So in this case, this S is your shaft, even though I called it the stator in the earlier case. Now this is the part which is rotating, and this is the outer casing which is constant. So this is rotation, and I mean the fluid will try to apply a friction force in this direction because it is rotating like this, and that's how you would experience these external shear stresses. But because you have a bearing, they are assumed to be negligible between them. Okay, so after this is quite easy. You have to apply the equilibrium first. Okay, that would be balancing the moments about this point A. Okay, so you would have MA, you would have minus 8 Newton meter, you would have minus 8 Newton meter equal to 0, and then you would also have to have a twisting moment in the section AB and BC. So in this, so MA would be, so this is the moment applied by the motor. Okay, so MAB would be what, 16 Newton meter, and what would be the MAB, and what would be the twisting moment in the segment BC? That would be equal to 8 Newton meter. Okay, in this segment BC, the twisting moment would be different than in this one. Okay. Okay, so once this is done, that's the first step. The first, I mean, can you figure out really why MBC should be 8 Newton meter? I mean, you should take a pause and figure that out. Why it is, why the MBC is 8 Newton meter. Okay, so for this you might have to draw that, just like you had drawn the bending moment and the axial force diagram for the whole segment, you may have to draw an MT diagram for the whole segment. So there you would start from here and make a break over here and this break over there. So you have to take two segments. First of all, take X from 0 to somewhere in middle, then take your other X from, say, here to somewhere between this and this, and then try to do the moment balance. That's how you should do this. Okay, so you should be able to draw this MAB and MBC on a diagram. Come like this. Okay, so what about the geometric compatibility of the two parts AB and AC? So the total twist phi AC will be equal to the twist AB, okay, plus BC. That's straightforward. Okay, and this is something which you can observe by twisting, say, a eraser, which you can easily see. or if you can find something else which is easier to visualize. So the total twist will be the same, will be the summation of those individual parts of it. I mean, if you take it into three, divide your uh, shaft into three parts, then you would have, I mean, if you have this and you sort of twist it, then if you divide it hypothetically into three parts, the total twist which would be there between this point and this point would be the summation of between this point and this point, this point and this point, this point and this point. Okay, so this is a geometric compatibility which is written just by observation, and after this you have to just use the load deformation relation, which is this one. So you have to again use it on two shafts. First you have to use it on AB, this equation, and then you have to use it on BC. So then you would get the total angular twist, and you should also get the this value, shear stress. Shear stress, the maximum value is asked, so MAB is what you would be using. So it is asked only in this region. Okay, so the MAB is something which you have found out, I think 16 Newton meters, and IZ you can find out by the formula which you have over here. And this R, for this to be maximum, R has to be the outer radius. So that is what 1 centimeter is the dia to 0.5 centimeters. So you will have to take this as 0.5 centimeters. Okay, so that's where you would do this particular problem. And there is also an example 6.2 which I am leaving out for you to study. This is like a small extension to this problem, but you should do this. Okay, so that we can move to the next topic. So 6.2 is left for you to do. And okay, so then the next topic which we would want to study is 6.6, and that is called the torsion of elastic hollow circular shaft. Okay, so many a times your shaft may not be solid throughout. It may have a hole inside it, and this can be used, say if you want to pass a fluid through it, you want to pass electrical wires through it. Okay, so there are many reasons why you would want, or a gas through it. Okay.